Let's now proceed to learn how to name ketones. Similar to the aldehydes, when we are naming ketones, we still have the prefix, root, and ending format for writing the name. And when it comes to this, let's understand that the prefix, like we saw before, this is going to be the location and name of the substituent that you have in the molecule. Or if you have multiple substituents, understand that you have to put them in alphabetical order, like we learned before. Then, when it comes to the root is going to be what we've seen before. This is going to be the alkane name of the longest continuous chain of carbon atoms. And you're going to omit the E ending in the word. Next, the ending for a ketone is the suffix "-one". Let's look at the example on the left. When we look at what is the longest carbon chain in that ketone, we can say carbon 1, 2, 3, 4, 5. Or we can say carbon 1, 2, 3, 4, 5. Notice that I'm numbering the longest continuous chain of carbon atoms starting from the end that it is closest to the C double bond O, because that's how I start numbering in ketones. So if I do that, then I can select this as the longest carbon chain. And when I write the numbering, this is carbon 1, this is carbon 2, this is carbon 3, carbon 4, and lastly, carbon 5. Since I have 5 carbons in my ketone, the root name is going to be pentane. But remember that we have to omit the E ending. So let me just erase it. And then we have to put the correct ending because we have a ketone, which means that we have an "-one" ending. So that parent chain is going to be pentanone. Now, different from the aldehydes, when it comes to the ketones, let's establish that before the word for the root, I need to give the location of the carbon at the C double bond O. So that means that when I write the name for this ketone, I'm going to put 2-pentanone to symbolize that the C double bond O is on carbon 2. Then, previous to that, we have to put the prefix. Specifically in this molecule on carbon 4, we only have one substituent. So on carbon 4, I have a methyl group. Remember that every time we have numbers and letters, we use a hyphen to separate them. So the correct name for this molecule is 4-methyl-2-pentanone. Ketones can be cyclic. And when ketones are cyclic, the rules that I set up for going from structure to writing the name are going to be like I just outlined for you guys. First, we're going to find the root, which is the alkane name of the longest continuous chain of carbon atoms. In a cyclic ketone, the cyclic structure will be the longest continuous chain of carbon atoms. That means that in this molecule, since I have 1, 2, 3, 4, 5, 6 carbons, that means that the alkane name for the root is going to be cyclohexane. The E must be omitted. Next, we have to put the correct ending, which for a ketone is -one. So cyclohexanone is going to be specifically this part of the molecule. When you have a cyclic ketone, the C double bond O is carbon 1. Then you have to number the ring system clockwise or counterclockwise to give the substituent the correct numbering, which is the lowest number. In this molecule, it doesn't matter if I go counterclockwise or clockwise, my substituent is going to be on position 4, because this is carbon number 2, this is 3, this is 4, this is 5, and this is 6. So out of carbon 4, we actually have an ethyl group. So to finish the name for this molecule, we're going to write 4-ethyl cyclohexanone. And these are the rules for naming aldehydes and ketones. Make sure that you practice also going from name to chemical formula in the provided worksheets. Let's now proceed to talk about the physical properties for aldehydes and ketones. The lack of a hydrogen on the oxygen prevents the formation of hydrogen bonds between two aldehyde molecules. The boiling points of pure aldehydes and ketones are expected to be lower than those of alcohols with similar molecular weights, but their boiling points are going to be higher than alkanes. In table 10.2, we have a comparison of physical properties. You can see the class of molecules, an example, the chemical formula. Then we have the molecular weight, boiling point, and water solubility. We can observe that if we compare an alkane, an aldehyde, a ketone, or an alcohol, overall, we see that the boiling point for the alcohol is the highest compared to the other functional groups. One of the reasons why this is true is because between two alcohol molecules, they are going to have the strongest attractive force, which is hydrogen bonding. If we have ketones or aldehydes interacting with themselves, the major attractive force that we will have in those molecules is going to be dipole-dipole. The reason why we are going to find in ketones and in aldehydes dipole-dipole attractions is because the C double bond O bond is polar. So in these molecules, since we have a polar bond, and overall, we see that there's differences in specifically the groups that are surrounding them. And when it comes to attractive forces, they have dipole-dipole attractions. That explains that the boiling point of these molecules is going to be higher than alkanes. Because in the case of alkenes, what we have is nonpolar molecules, which means that in a solution of butane, even though it's close in molecular weight to propanol and propanone, we see that overall the boiling point is low. And it is simply by the fact that dispersion forces is the major attractive force found in the molecule. So remember that whenever you're looking and trying to suggest what would be the molecule that will have the highest boiling point is going to be the one that has the strongest attractive force present in the molecule. Now let's understand that even though hydrogens to themselves and ketones to themselves do not hydrogen bond, these two functional groups can hydrogen bond specifically with water in solution. Water is a polar solvent and can be expected to be effective in dissolving some molecules that have polar groups, including polar carbonyl groups. So besides the dipole-dipole interaction that we actually find in aldehydes to themselves, in ketones to themselves, what happens is, if I zoom in to the images that we have on the right side of the slide, is that in the case, for example, of the ketone that we have on letter A, there is hydrogen bonding events happening between the ketone and the water. Now, these hydrogen bonding events are going to be specifically H bond accepting roles, specifically for the ketone, because what happens is that since the ketone has a polar bond, as you can see here by the delta plus, delta minus, illustrated between the carbon double bond to oxygen. And since oxygen is one of those three electronegative atoms that can be involved in hydrogen bonding, that's why we see a hydrogen bond of our ketone with water. Remember that the three atoms that are able to undergo hydrogen bonding events is going to be fluorine, oxygen, and nitrogen. Now, one of the things is that whenever we have aldehydes and ketones that have a little bit of a larger um, carbon chain, they tend to be less soluble in water. So, for example, if we look at the ketone that we have here, which has 1, 2, 3, 4, 5, 6, 7 carbons, one of the things that it is observed is that when it comes to those, they do not tend to be soluble in water, even though they can potentially have hydrogen bonding events occurring as it is symbolized by these dotted lines here. And this is the reason. When it comes to aldehydes and ketones that have 5 carbons or more, since these areas of the molecule are highly nonpolar, what we observe is that when the molecule is in the presence of water, London dispersion forces between the molecule to itself are going to be the prevalent attractive force in the solution. And because the molecules are going to have this long stretch of carbon atoms, we tend to observe that when you have 5 carbons or more in aldehydes or ketones, they tend to be insoluble in water, even though potentially they can have the formation of hydrogen bonding events in water. So remember that the trend of having 5 carbons or more in a particular molecule and that relating to solubility applies to both aldehydes and ketones. 5 carbons or more, there's a reduced solubility of the molecule. Now we're going to proceed to talk about the reactions of aldehydes and ketones. The first reaction that we're going to talk about is hydrogenation of aldehydes and ketones with the use of a catalyst. Hydrogenation is a reaction that we learn in chapter 8. And specifically in chapter 8, we learn that when it comes to hydrogenation, this is when an alkene gets reacted with H2 in the presence of a catalyst that could be platinum, as you can see in the slide. It could be palladium, or it could be nickel. What happens in this addition reaction is that we are going to break one of the bonds in the double bond, and each carbon atom that used to be double bonded will be receiving a hydrogen. Since we're adding atoms, that's why this is called an addition reaction. When it comes to the addition of hydrogen to an aldehyde, let's understand that something very similar is going to happen. Specifically, is going to happen at the carbonyl. So let me just zoom in so we look at this reaction closely. So the addition of the hydrogens will happen at the carbonyl. And the atoms that used to be double bonded in the carbonyl, meaning the carbon and the oxygen, each of them, upon hydrogenation of the aldehyde, will receive a hydrogen. So we observe that the oxygen atom received the hydrogen, and the carbon that used to be in the carbonyl also receives a hydrogen. So in terms of functional groups, when an aldehyde undergoes hydrogenation, what we're going to form is a primary alcohol. Next, ketones can also be hydrogenated. Upon the hydrogenation of a ketone, let's understand that we are going to similarly add atoms on the carbon and the oxygen that were part of the carbonyl in the ketone. We can observe here that what happens overall in our molecule is that one of the two bonds in the double bond is going to be broken, and then the oxygen in the carbonyl is going to receive a hydrogen, and then the carbon in the carbonyl is going to receive the hydrogen. So whenever we are hydrogenating a ketone, what we form is a secondary alcohol. When it comes to the hydrogenation reaction of aldehyde and ketones, understand that the example that we just saw, it is called a reduction reaction. And the reason why we call it a reduction reaction is because you have less bonds between carbon and oxygen. Additionally, in order to make that primary alcohol that comes from the aldehyde or that secondary alcohol that comes from the ketone, we can have other reagents to perform that reaction. Specifically, we see here that the letter R is being utilized to represent that reducing reagent that will take the aldehyde to the primary alcohol and the ketone to the secondary alcohol. Remember that these reactions are not any different than the hydrogenation that we just observed. If we pay close attention to our functional groups, in the case of the aldehyde, the carbon in the carbonyl and the oxygen in the carbonyl, you're going to go from a double bond to a single bond. Next, and let me just highlight the atoms so you can follow. The oxygen that used to be in the carbonyl now is going to be bonded to an incoming hydrogen. The carbon atom that used to be in the carbonyl now is going to be bonded to an additional hydrogen. So reduction of aldehydes and ketones also makes a primary alcohol. Or I should specify, let me clarify that. Reduction of an aldehyde will specifically form a primary alcohol. Because as we're going to see now, if we start with a ketone, meaning a C double bond oxygen, and on either side I have carbon chains, upon reduction, what's going to happen, and let me just highlight the atoms. The carbon in the carbonyl will receive a hydrogen. The oxygen in the carbonyl will receive a hydrogen. So when we are reducing a ketone, what we make is a secondary alcohol. In exams and in the worksheet, we are not going to see the letter R representing that we are reducing aldehydes and ketones. Reagents like sodium borohydride and lithium aluminum hydride are what is represented by the capital letter R. So whenever you see an aldehyde reacting with NABH4 or LiAlH4, that's going to represent the reduction from aldehyde to primary alcohol. And similarly, if you have a ketone, those two reagents are going to then produce a secondary alcohol from the ketone that we started with.